So from now on we'll actually not just deal with what is the physics, what is the background of the things that we are dealing with when we do crystallography, but we'll actually deal with what happens when we do a crystallographic experiment. And the first handout for that one is data collection. That is what you do if you want to do crystallography, right? You need to collect data. What data collection really is, it is the measurement of diffracted beams, right? Because we have by now established that the position of the diffracted beams tells you about the unit cell size and shape, plus the absences of reflections in this regular pattern actually tell you something about translational symmetry elements. Remember, all translational symmetry elements will actually give you systematic absences. In addition, we've established in handout 9 that the intensity of the beams is really related to where what type of atom sits in the unit cell, because that is given by the structure factors, and those are the sum of all Fj, and Fj of course depends on the atom, times e to the I2 pi hxj plus kyj plus lzj. So it depends on the position of the atom too. Now, that is the very basic idea. You need to measure diffracted beams in order to do a diffraction experiment. However, there's a little bit more, of course, to that. First of all, you need to generate some beams, right? You need a source. Secondly, you need to put your sample properly into that beam. And thirdly, you then need to actually detect your diffracted beams. Okay, and we'll be talking about all of these today. So, here are the important parts of your experimental setup. Radiation source. We'll be talking a little bit about X-ray tubes and about special sources, synchrotrons and neutrons. How do you mount your specimen? For that matter, what is your specimen? Is it a single crystal? Is it a powder? What kind of detector are you using? There are a lot of options. Film is one of the oldest ones, image plates, point detectors, area detectors. Now obviously anything that detects more than one reflection at a time is faster. So there's a speed difference between these detectors. One thing that a lot of people forget is the experimental method also matters, okay, because this one determines how much of reciprocal space you can actually image and how you do it, okay. Certain experimental setups have inherent limitations, and in some cases within those limitations you can do everything you want to do, so go for it. But other times you may not be able to actually accept these limitations. You need to change your experimental setup. Okay, so that's something else to consider. What kind of data can you get? Here's one of them. Okay, how many reflections do you actually need? And that's a good question because we haven't talked about that at all, right? Well, we certainly have learned in math that if we have a set of simultaneous linear equations, we need about one observable per parameter, right? Everybody has heard that before. However, we don't have linear equations in crystallography, do we? We have E functions, stuff like that, complex E functions. So we need more than one observation per parameter. Plus, of course, if you have several, you know, you're just a little more trusting in what you get out. So as a rule of thumb in crystallography, you should have about 10 reflections for each parameter that you want to determine. Okay? Now, how many reflections can you actually measure? Well, the first inclination that people might have is to say, well, we can measure as many as we want, right? Well, theoretically, sure, they all exist, right? Practically, some of them might be a bit weak, so it might be difficult to measure. The other thing is, remember that handout with the fourth condition, the wavelength condition, the Ewald sphere? There's a limitation how many of these reflections you can actually observe with a given experimental setup. Because all that you image in reciprocal space is the sphere with a radius of 2 over lambda. Okay? That is it. You cannot measure more than that in reciprocal space. Now, that means you can calculate the maximum number of reflections that you can measure. Okay? And here's the equation that gives the maximum number of reflections n that you can measure. It has some geometrical factors in, 4 pi over 3. It depends on the unit cell volume, because that determines how far things are spaced, right? The larger your real space lattice constants, the closer together the points are in reciprocal space. So the larger the volume, the more reflections you can measure. Divided by n, where n is the number of lattice points in the unit cell, and lambda cubed. So the wavelength has a very big contribution to this. Goes in to the power 3. Okay. Now, this takes into account absences from lattice centering. Okay, because the number of lattice points corresponds to C centering, F centering, I centering, right? Do keep in mind, this is the maximum number of reflections that you could theoretically measure. If you have other systematic absences, like that 2-1 screw that we did on the exam, they also give you absences. Okay, quite a few of the reflections disappear, but they are not actually accounted for in this equation. So you could have a lot less reflections measured than this equation suggests as the maximum number. This is what you want to look at if you want to decide whether a certain wavelength will do for your experiment. Okay. Now I can already tell you, if you guys are working on proteins, you'll have enough reflections probably. Okay. If you guys work on a small molecule, this cartoon gives you some idea of what the difference between the wavelengths is. This is of course not really to scale on anything, okay? I don't define a scale, but here's a comparison. If this is the portion of reciprocal space that you can measure with chromium K alpha, then this is the portion of reciprocal space that you can measure with copper K alpha, and this is what you can measure with molybdenum K alpha, where the wavelengths are 2.3, 1.5 and 0.7 angstroms. That's a huge difference, okay? This kind of just gives you the face-on view. Of course, this is three-dimensional space that you measure, right? So it makes a big difference. This also shows you why most small molecule crystallographers will be measuring with molybdenum, okay? You see a lot more reflections. So, let's look at the different parts of our experimental setup, and let's start with the first one, radiation sources. Here are the 3 most commonly used radiation sources. The most commonly used one is the X-ray tube, because that is your lab X-ray source, and most people do their experiments in their lab. What this is a so-called line source with a white background. We'll see a couple of slides down what exactly that means. One of the main things to keep in mind is, compared to the other methods, an X-ray tube has pretty low flux. It does make X-rays. It does make enough that if you stuck your fingers in the beam you would get hurt, okay? But compared to what is possible, it really has pretty low flux. If you want higher flux, the synchrotron is your friend, okay? Synchrotron radiation can have very high flux. Synchrotron radiation is actually not a line source, it is white tunable radiation. Okay? So that means you can choose your wavelength. While usually we are kind of bound by the element in our target in a lab X-ray source. And then of course there are neutrons. You can use 2 sources, a nuclear reactor or a spallation source, to produce neutrons. This is certainly the most expensive method on this scale. Okay? However, there are times when neutrons can be very useful. For example, if you work with a lot of light elements, neutrons are actually more sensitive to light elements compared to heavy elements than X-rays, okay? Or if you have neighboring elements. So, let's start to look back at the first source. We've already looked at the X-ray cathode a little bit. Here's a little reminder. Here's your X-ray tube. You have a filament, you run electrons through it, you have a high voltage that accelerates the electrons towards your metal target, where they knock out core electrons. And that is how you then produce X-rays. Now, let's look in a little more detail at what determines what the wavelength of these X-rays is. Here's a little picture, okay? So, we hit the metal target with a high energy electron beam. 2 things happen, okay? One is the electrons that hit the target are decelerated. It's pretty logical, right? When the electron is decelerated, it loses energy, so we need to get rid of that energy somehow. And that is the white background of a lab X-ray tube. Okay? It's called Bremsstrahlung, which is the German word for braking radiation. And this is what you get. Okay? This is a spectrum intensity versus wavelength. Some kind of a hump, white background. But that's not really what we use when we work with a lab X-ray tube. Okay? What we work with is, in many cases, the electron that hits the target will eject a core electron. Of course, atoms aren't really happy when they have a hole in their core electron shell, right? So what will happen is that one of the outer electrons will fall down. Now we all know that the different electronic shells have different energy, right? Which means the energy difference is emitted. Guess what the energy difference is like? It's right in the X-ray region. Okay? That is why we get emission of X-rays. And this little cartoon actually shows you how our radiation is named. If an electron is ejected from the K shell, and we have an electron drop down into the K shell, we certainly call that K something, radiation. If it drops down from the closest neighboring shell, we call it K alpha. So that's an L to K transition. If an electron from the M shell falls down to the K shell, we call that K beta. So that is the second shell over from the K shell. You then sometimes find little subscripts. Okay? Whoa, that projector is really going bad, isn't it? Hey. Last. What you find often is that you, for example, hear people talk about copper K alpha 1, copper K alpha 2. Well, the reason for that is the L shell has more than one energy level, right? If you think back to your orbitals. And they are very close together in energy. So what you get is several lines that are very close together in wavelength. Okay, and if you ever look at tables of characteristic wavelengths, you will actually find that. Copper, for that matter, copper K alpha 1 and K alpha 2 are often not even separated when you do a diffraction experiment. So that's your X-ray tube. How about a synchrotron? Yes?
How do the shells correspond to like the K, D, S, and...
The K shell is the first shell, so it goes with the periodic table, okay? The L shell is the second shell, and so on. So a lot of them have multiple orbitals. The first one only has S, but the second shell then has S and P, and you keep going like that.
So why would one ever come down from the outer shell?
Because a hole in the core shell is not stable. That's the lowest energy level, right? That's what the atom would usually fill first. So if you happen to knock that electron out, something else will go down to that lowest energy level.
So wouldn't alpha always be closer than the beta?
The alpha is always closer, but sometimes it just so happens that one of these falls down. The K alpha line is usually the strongest line, so you're absolutely right about that. That is why most diffraction experiments are done with the K alpha line. If you look at the tables like the one that you were given on the exam, the K alpha is the strongest line. But the other ones also happen, okay? There's a little bit of statistics involved there and all kinds of quantum probably. So all of these transitions do happen, but the K alpha is the strongest one. More questions about the X-ray tube? In that case, let's move on to the synchrotron. Synchrotron radiation takes a little more to produce than an X-ray tube. Okay? This is a very simplified schematic of what a synchrotron looks like, but it shows you all the important pieces. You have a linear accelerator. That is basically a linear piece of equipment where electrons are accelerated by a really high voltage to really high speeds. You then feed them into something that is called a booster ring. And the booster ring has only one job, and that is to accelerate these electrons even further. So what you have in these rings is magnets that bend the path of the electron beam and thus accelerate them. Once the electrons have reached close to the speed of light, they are fed in the synchrotron or storage ring. Okay? And they keep circulating there. That is the place where sometimes the first people get suspicious and say, okay, they circulate there. Why on earth would an electron in its right mind circulate? Any ideas? You got to use some kind of magnets to actually make sure that the electron stays on its circular path. Exactly. So, this is often drawn as a ring. When people give you a schematic, in real life it's actually really a polygon, okay? This is a slightly more complex picture. It shows you a few of the components involved in a synchrotron. Don't memorize these, okay? This is just for your benefit so that you get some idea of how these machines actually work. One of the important things is what you see here. It's called a bending magnet. You can already guess what it does by its name. It bends the path of the electron beam. You also have a whole bunch of vacuum pumps around here, okay, different types. Because if your electrons were flying in air, how far would they make it? Until they hit the next atom, right? And that would not be very far. So you need to keep things under vacuum if you want to have a stable electron beam. You then have certain things here that are called insertion devices. This one is a wiggler, okay? They actually make even more X-rays. And then you have certain things like RF cavities where you actually give the electron beam the energy back that it loses every time it circulates around the synchrotron. Because if you want a stable beam, you want it to look the same way every time it comes around. Now, why are X-rays produced? Well, remember that I said that the electrons are circulating close to the speed of light? Can we accelerate them any further at that point in time? No, right? So they can't get faster, but if we use a magnet to make the electron path bend, then we are accelerating them, right? So we accelerate the electron, we put energy in, but the electron can't gain kinetic energy. That means the energy has to go somewhere, right? Because we always have to preserve the total energy of a system. Well, what happens is the excess energy is given off as X-ray radiation. Okay? So every time you bend that electron path, you get X-ray radiation out. That is how a synchrotron works. Which means at each bending magnet, you get X-rays. You can do experiments. Okay? And these wigglers really do nothing but wiggle the electron beam path, which means the electrons once again are accelerated and you make more X-rays. There will be a handout further on where we will actually talk in more detail about what that is like, okay? What that means, how that works. What does a synchrotron look like in real life? Here's the closest one to our university, the Advanced Photon Source, which is located at Argonne National Lab just south of Chicago. And this is an aerial. This is the synchrotron storage ring. Okay? And it looks fairly circular. It is actually composed of a whole bunch of bending magnets, of course. Here's your LINAC in the middle. And the booster ring is actually underground, so you can't see it. This is the world's second most powerful synchrotron when it comes to the ring size. So we have one of those big toys just around the corner, about 4 hours driving distance. And quite a lot of research groups here go to the synchrotron to do specialized experiments. Okay? So this is not just something that is totally out of what you might be using once you do your PhD research here. Now, why do we go to these things? Why do we take a 4-hour drive and do our experiments there instead of here? Well, here is your energy spectrum of synchrotron radiation. Okay? These are beamlines at a bunch of different synchrotrons. National Synchrotron Light Source at Brookhaven National Lab out on Long Island. This is a typical bending magnet there. This is the energy spectrum that you get when you use what is called an insertion device. This is actually a wiggler, okay, one of those things that wiggles the electron beam. Here is what the Advanced Photon Source gives you on a bending magnet. Quite a difference, right? This is of course an energy scale, so you can see a lot of high energy X-rays. This is what you can do at the advanced photon source if you use one of those insertion devices. That is pretty huge, okay, and this is a log scale, make no mistakes. There's one other synchrotron on here, CHESS, which is at Cornell in Ithaca. That is actually where my group sometimes does measurements. Where would copper K alpha be on this scale? Well, copper K alpha is 8 kV, so that's down here. And it would probably be somewhere around here on this graph, in that lower corner. You have orders of magnitude more intensity at a synchrotron source, and you have a whole wide range of wavelengths that you can choose from. Okay? There are a couple of additional advantages. Your synchrotron radiation comes plane polarized, so you can do specialized experiments. You don't have to worry as much about collimation because it is intrinsically collimated. One other important thing is it has a time structure. And the reason for that is what you have here are electron bunches that are circulating around the storage ring. Okay? You know what the spacing between those bunches is. So you can hit your sample with an X-ray pulse and basically do kinetic studies. What changes at that point in time. Okay? So there are a lot of very different experiments that can be done in a synchrotron that you cannot do in-house. And that's why we have these facilities, and they are actually very popular. Now, the third type of radiation source are neutron sources. And as I said, you have two options, reactors or spallation sources. A reactor, most people probably have some idea of how that one works, because we all have heard about nuclear reactors, right? You have a nuclear chain reaction, and that one produces neutrons. And in most cases, the neutrons are only used to keep the chain reaction going, and a bunch of them have to be absorbed so that things don't get out of control. Or alternatively, you can actually use these neutrons and do diffraction experiments. So there are actually research reactors where people produce neutrons to use them in diffraction. The neutrons that are produced are pretty fast, so you need a moderator to slow them down so that you can use them in diffraction, because if they are too fast, they'll go straight through your material. They won't ever interact with it. And you get a wavelength distribution that corresponds to whatever your moderator is. Okay, it's the thermal equilibrium distribution of your moderator. Now that means that what you do at this point in time is fairly similar to an X-ray experiment. You need a monochromator, you choose your wavelength, and you take a small cut somewhere out of this thermal equilibrium distribution, and those are the neutrons that you use. So the problem is you throw away a lot of neutrons. Okay, and it works pretty well, and you have a pretty decent peak flux. Okay, but that is why people started developing spallation sources. A spallation source is a source where you take a metal target and you bombard it with neutrons. And what happens when you bombard the target with neutrons, actually with protons usually, when you bombard it with protons, you eject neutrons out of the target. So what you get is a pulsed source. Okay. Whenever a proton pulse hits the target, you get a pulse of neutrons out. You get a very different wavelength distribution, okay, if you look at this versus this, than you get with a reactor. You have overall a lower flux than you have over here, okay, but this has a time structure. You get a neutron pulse out. And that actually means that people can use all the neutrons in this source. And that's something that is often difficult to grasp at the beginning, okay? How can you use all the neutrons? You have all these different wavelengths. Well, what happens is a neutron is a particle with mass, right? The mass of a neutron is not negligible. So, that means that the wavelength is related to the speed at which the neutron travels. The brass relationship, right? So, neutrons of different wavelengths that leave the target at the same time will arrive at the sample at different times. What you now have is a bunch of detectors that do not only detect when the neutron hits them, but also not only that the neutron hits them, but also when the neutron hits them. So what you do is a so-called time of flight experiment. Okay? So you collect all the neutrons of all the different wavelengths, and you discriminate the wavelength by the time at which they arrive at the detector. Has the advantage that you can use all of the neutrons that you produce. You do not have to throw any of them out. So, much more efficient. Another reason why people have developed spallation sources is you can go to higher powers than you can with a reactor. Because let's face it, there's a limit to how big of a reactor we want to build, right? It's a safety issue. The newest addition in the line of spallation neutron sources is actually at Oak Ridge National Lab, and it's called the spallation neutron source, or SNS. When I started teaching this class, they had broken ground, but they hadn't gone much further than that. This was the design, so they basically had a linear accelerator, and they had their target, once again accumulator ring, and then, well actually that is for their particles that will hit the target, and then you get all these stations around the target. And the target is actually a liquid metal, okay, because then you can dissipate the heat better. So you have a big chunk of mercury in that target. Here was the artist's rendering of what this was supposed to look like, okay. Your LINAC, your ring, your target station, future second target building, and then an experimental, basically a big office building with a lot of labs to support all the stuff that was going to go on here. What does it look like nowadays? Well, construction is actually finished. Here is an aerial of the site, and as you can see, they pretty closely followed the artist on that one. And as a matter of fact, as of a year ago, the spallation neutron source at Oak Ridge has become the most powerful pulse spallation source in the world. That was when they are at 180 kilowatts. So they overtook the previous most powerful spallation source with that. What's the goal of this spallation source? 1.4 megawatt. So not only is it already the most powerful source, they are planning to be a heck of a lot more powerful than the other sources that have been built previously. And there are some other countries that are thinking about building new spallation sources, so there will be more competition again in the future. But it will be a very powerful source. Yes?
How does one add more power to the source besides just feeding more power to it?
Basically part of that is what kind of a pulse can you hit on the target. Okay, and the main limitation there was always how fast can you dissipate heat. And that is the reason why they are going with a big liquid mercury target, because then you can circulate the metal, you always expose new things. One of the things is neutron guides have improved, so there are quite a few improvements. And we'll also have more about that one once we go to the specialized synchrotrons and neutrons handout. But the nice thing with this source was, this was the first time that neutrons could compete with some of the older synchrotron sources in terms of the types of experiments that you can do there with respect to the flux that you get on your sample. Okay, so this was really a very big step when that one was built. And the instruments are now slowly coming online. Several of them are already available for users. Several other ones are scheduled to become available over the next couple of years. So some of you might even go there. Now, why would people use neutrons? Looks like it's a heck of a lot more effort to produce neutrons than it is to produce X-rays, right? And for that matter, you have all kinds of safety issues around neutron reactors. However, they do give you a lot of advantages in some experiments. Big difference that we already touched on before is neutrons are scattered by nuclei, not by the electrons, right? What does that mean? Well, first of all, it means the form factor will not fall off as rapidly with angle, because the nucleus is much smaller than the electron cloud. Okay. Second thing is, the thermal motion of your nucleus is a lot like the thermal motion of the electron cloud. So, what that overall means is you usually get better data at high angles. And if you think back, that means you get better data to smaller d spacings, and that means better resolution, right? So that's why that could be important. Another very big one is your neutron form factors, which is the same as the scattering factor that we talk about with X-rays, does not show a strong dependence on the atomic number like the X-ray scattering factor does. Okay? That means, in comparison to X-rays, you really see the light elements better. You can sometimes distinguish neighboring elements very well, and in specialized cases you can even distinguish isotopes of the same element because the nuclear structure changes. So they look different to neutrons. Okay? Another reason why people do neutron diffraction is neutrons actually interact with magnetic moments. So you can determine the magnetic structure of your material using neutron diffraction. That is actually one of the very big reasons why people use neutron sources. Another one is most elements will not strongly absorb neutrons, while heavier elements absorb X-rays quite strongly, which means you can use pretty big samples. Now that can be a plus or a minus. If you work with really small research samples, that sucks, okay? If you are an engineer and you work with big pieces, some kind of, functional pieces, and you want to look at something in those pieces, hey, this rules, because you can just put that piece right in the beam and you can go through it. Now, this graph actually shows you what I mean with neutrons are more sensitive to the light elements compared to the X-rays. Now, that doesn't mean that neutrons are much more sensitive than X-rays. The main difference is the neutron form factors don't change a lot with atomic number. So in a relative way, neutrons are more sensitive to the light elements because they look fairly similar to the heavy elements when it comes to the form factor. While for X-rays, you have the strong dependence on atomic number, on the number of electrons. Okay? Neutron form factor varies almost erratically around this line. And one of the things that you can see is it can be positive or it can be negative. That's something that is different from X-rays. So if you do neutron maps, okay, where you look at scattering power, there are actually elements that have negative scattering power. Okay? Here's an example of what I was talking about with neighboring, with the same element can look different with different isotopes. Nickel 58, nickel 62, very different form factors. Okay? Hydrogen, for that matter, deuterium, actually has a positive form factor. You can make use of that. If you want to, you can just make all of your hydrogen disappear from the scattering by using the appropriate amounts of hydrogen and deuterium. The average form factor becomes 0. Okay? So there are tricks you can play with neutrons that you cannot play with X-rays. So, those were our radiation sources. Let's look at what do we actually do with our specimen, with our sample. So I said, two options, powder or single crystal in most cases. So let's start with the powder, because the project that we'll be dealing with is going to be a powder project. What should a powder be? Well, the perfect powder is an infinite number of randomly oriented small crystallites. That's a short definition of it. You want pretty small particles, okay? And what does that mean? If you have a powder that has particles that are bigger than 20 microns, go grind. Okay? It's not a good powder sample. Something where you want to look for a specialized diffractometer and do single crystal studies. That's at least my opinion. Ideal powders are about 1 to 5 microns. How do you achieve that? Well, one thing is you grind. Okay? Another thing that can help you is there are so-called sieves. These are basically meshes of different size holes that you can stack, and then you throw your sample in at the top. You kind of shake it, or you might even try to grind on the sieve, and only the things that go through are below a certain size, below the mesh size of your sieve. Okay? So that's a way of actually figuring out what your particle size is, and to sieve out all the particles that are too big that you don't want to use. Now, some people actually get overzealous and they do a really good job grinding. So, one word of warning, do not overgrind your sample. okay? Because what happens then is, you could be going below your ideal size, or you could be introducing a lot of defects in your powder if you're too harsh to it, okay? What that does is, it leads to all kinds of ugly peak broadening that makes your data treatment much more difficult. So, you don't want huge particles, but you do not want to overgrind your sample either. And that's where those sieves really come in handy, okay? They allow you to judge how far you've ground. Sample morphology could be an important issue, okay? If you have platelets, if you have rods, chances are you'll get something that is called preferred orientation. Your random orientation will not be given. Because let's face it, how many times have you seen rods stand up on their end? They usually don't do that, do they? So that's an important consideration, okay? Now, how do you usually mount your sample? There are two very common ways of mounting them. One is the so-called flat plate sample. Basically, you have a flat plate of a sample, and you stick it in, and like in the little drawing of Bragg's law, you bounce your X-rays off the surface of that sample. The second commonly used one is actually a capillary measurement, okay? Capillaries give you some benefits. You can actually protect the sample from air. You could actually run a sample in a mother liquor, for example, for proteins, okay? Special environments. Of course, what you need to watch out for is what's the absorption of your sample, because now you go through the capillary, okay? If you have a sample with heavy elements, you need very, very narrow capillaries, and that's no fun to pack. If you have something organic, capillaries are actually quite easy to handle. So, that's how we deal with our powder. How about single crystals? Well, if you work on small molecules and you go down to a crystallographer and you say, okay, what kind of crystal do you want? Usually what they tell you is that about 50 to 200 micron in size works for most samples. And you can do more precise predictions with respect to what atoms do you have in your sample, how well should it scatter, how much should it absorb, you know, what kind of size you want. But as a rule of thumb, if you have something in this size range, you should be able to do your experiment, okay? This is for a lab source. At a synchrotron, you can run much smaller crystals, okay? I have heard that people have run crystals that were 1 micron by 1 micron by 1 micron as a single crystal at a synchrotron. And so you start wondering, what's a powder, what's a single crystal, okay? That would qualify as a pretty good powder. Can you do it with a protein on a 1 micron crystal? No. Okay, that's not a single crystal for a protein. But for small molecules, it could sometimes actually work. Now, I've never pushed it quite that far, but when I was a postdoc, I made a sample. That was a pretty nice fine powder. And I actually ran my powder data. I could get some indexing. I could not go anywhere with it. And I tried to grow crystals, and the stuff was always between 5 and 10 microns. No chance. So I actually went to CHES because I was on campus with a synchrotron, right? And I ran a crystal that was about 7.5 micron. It was no problem at all to solve the structure of that 7.5 micron crystal with synchrotron data, okay? So yes, these things are possible. So if you get desperate, synchrotrons could be an option. They can actually really help you out in that respect. Now, so size matters in the lab. If you have access to a synchrotron, size is no longer as crucial, okay? But what else is important? Well, the quality of your crystal is actually really important. Never mind whether you go to a synchrotron or to a lab source. And this statement seems almost trivial, okay? Only true single crystals will give a true single crystal diffraction pattern. Okay, that's a no-brainer, right? But it's a very important statement to keep in mind, because you wouldn't believe how many times people mount something that is not a true single crystal. What do you get? Overlapping diffraction patterns, okay? Now, the computer doesn't have some kind of color labeling that says, oh, this was from one of your crystals that you have on here, this is from the other one. The computer doesn't know. The computer assumes you as the user know what you're doing, and you give it a single crystal. The computer will try to deal with all that data. And in many cases it will fail miserably. Okay, so most of the time when you don't get a solution, the reason for that is crystal quality. You didn't give your system a true single crystal. Okay, how do you figure it out? It's tough, right? Well, first of all, you use a good microscope. You look at it closely. You inspect it. You make sure it looks pretty. We looked at those early pictures of crystals, right? Those were huge things. I agree. But on a small scale, that should hold true. A crystal should have faces. A crystal shouldn't look like there are two pieces grown together at odd angles. That's probably a twin, okay? Another way to do it is use polarizers. Because your whole crystal should extinguish at the same setting of the polarizers if it is one single crystal. If it is more than one single crystal, chances are your orientations are different and they will extinguish at different settings of your polarizers. So that really allows you to look at whether or not you have a single crystal. This takes a little bit of time to do. However, it's worth it instead of spending a few hours sticking stuff on the diffractometer and nothing indexing, okay? Now, if you really have a choice, pick a crystal that has about the same dimensions, the same length in all dimensions. The reason for that is it makes for a really easy absorption correction, okay? If your crystal has about the same length, never mind from which direction you hit it, it'll absorb the same way, never mind from which direction you hit it, so it becomes a constant. Is it going to be a killer if your crystal is not equal dimensions? No. You can do absorption corrections. It's just easier, if you have a choice, to use one that has equal dimensions. Does that make sense? Everybody now know what a perfect single crystal looks like? I hope you'll all find some in the course of your career. So, what do you do once you've found your perfect single crystal? Well, most of the time, you actually attach them to a glass fiber or you seal them inside a capillary. Capillaries are mainly used if you need a special environment or your sample is air sensitive. Traditional way are the glass fibers. In the old days, people used epoxy to glue their crystal to the glass fiber. And the main reason behind that was, once something is in epoxy, it's in epoxy. It's going to stay on the glass fiber. You didn't want things to fall off, okay? Nowadays, you will rarely find people using epoxy. And the reason for that is that in the old days, people used to run experiments at room temperature. Nowadays, very few experiments are run at room temperature. You usually run at liquid nitrogen, with a liquid nitrogen stream, at -100 centigrade, something like that, okay? Now, why do you run at low temperature? Well, it cuts down on thermal motion, so it makes your atoms look prettier, okay? They are more well defined. Don't have to worry as much about where they are located, especially for the light atoms. So that's an advantage. Problem with the epoxy is, in most cases, the epoxy on your crystal will expand at different rates. So you may be setting your crystal very nicely in epoxy at room temperature, but at low temperature, they don't match anymore. So things break apart where they touch, and your crystal may well fall off that glass fiber. It's pretty useless if you want to do a diffraction experiment on your crystal. So what you use instead is some kind of a grease or oil, okay? Because grease or oil at room temperature may leave the chance of the crystal falling off over time. But once you go to low temperature, what happens to grease? It gets pretty solid, right? We probably all know that from our kitchens. Cold grease solidifies usually. The same happens here. So you basically freeze the grease. The crystal is perfectly mounted. It's easy to take off after you're done with your experiment, okay? How you mount it exactly depends on what your crystal is, whether you need to protect it a little bit from air, and who teaches you. First way I was taught how to mount a crystal was, well, you need grease. And inevitably, almost everybody uses too much grease. Okay, you take that fiber, you dip it in some grease, you have too much grease on it. So our crystallographer at Georgia Tech used to say, here's an easy way to get enough grease. Take that glass fiber, do this. Just touch your forehead with it. If you have a small crystal, you pick up enough grease from your skin that the crystal will actually stick to it. And believe it or not, it actually works, okay? Of course I had to try that out. It works beautifully if you have a small crystal, okay? If your crystal is 200 micron, it might get tough. If your crystal is 50 micron, not a problem. And it makes sure you don't have too much grease on that glass fiber, okay? Because you really can't see the grease that you have on the glass fiber. That's how little you need in most cases. So, that's how we usually mount them. What we then do is we put that glass fiber or the capillary on what is called a goniometer head. And this is what a goniometer head looks like, okay? It's this intricate little thing that has a whole bunch of little screws that allow you to adjust where exactly a crystal is. Because remember, we will have to place it exactly at the center of the diffractometer. When we rotate it, it should not move, because otherwise we don't always hit it with our X-rays. So that's why you have all of these different degrees of freedom with which you can move that crystal up and down, you can tilt it, you can move it over, so that you can exactly center your crystal. Okay? So, that's how you mount your sample. Never thought there was so much to doing a diffraction experiment, did you? Let's talk about the last part of it, detector options. Oldest method to detect X-rays was photographic film. That's what Röntgen used, okay? When you hit film with X-rays, it will get dark. It's fairly sensitive, so it will detect fairly small amounts of X-rays. However, it has a pretty small dynamic range, and it's pretty difficult to get integrated intensities out of film. So what you find in the really old literature is that people report weak, strong, medium, kind of like with IR bands, okay? It's not useful if we really want to get a crystal structure, because we need precise intensities, right? That's what gives us the type and location of atoms. In the 80s, people developed image plates, which are actually fairly similar to film, okay, but a lot more powerful. They are much more sensitive. They have a very wide dynamic range, as a matter of fact about 6 orders of magnitude, so that's pretty good. They can be reused in contrast to film, so that's certainly an advantage. You can read them out with a computer. Ooh, now that's good, right? And what they are is, you have a photosensitive phosphor that is bound with an organic material so that it stays on the plate. When you hit that one with X-rays, you get a latent image. You can see it, okay? But there's a change occurring. And when you scan a laser across the surface, the places where that change occurred will emit stimulated emission, okay? And that is what you really detect. And we have instrumentation to detect very sensitively how much light comes out of something. So that's how this one works. And then you just use visible light to erase them. Now, here's an example of film, okay? Film is actually used both in powder and single crystal methods. Here's an example of a single crystal pattern. Here's an example of a powder pattern. This already shows you how people used to evaluate their data. You use a light box, and you look at things, and then you try to, you know, guesstimate your integrated intensities. That's also why a lot of crystallographers had very bad eyesight once they got older. Yes?
Between the two methods, the image plates, can those go bad like the X-ray film?
The image plates will go bad at some point in time, okay? Like everything, I mean, like a rechargeable battery, you have so many cycles, at some point in time things do get irreversible. Same holds true for image plates. One of the worst things is if people overexpose an image plate. It does have 6 orders of magnitude, but if you put a direct beam at a synchrotron on an image plate, that part of the image plate is going to be dead, okay? You can never erase that again. So yes, they will go bad, but if you treat them properly, they last a long time. Here's a little cartoon that shows you how the image plate works, okay? This one has a barium fluoride bromide with europium doping. The europium is what really will emit the fluorescence in the end. You hit it with X-rays, So it stores this image. Then when you scan a laser beam, you get the luminescence from your exposed areas, which you detect with a computer, pixel by pixel, okay? And then you use visible light to erase it. Disadvantages: takes you about 5 minutes to go through this process. So there's a turnaround time for image plates. But compared to film, quite nice. So what else can we do if we don't want to wait for 5 minutes? Well, we have point detectors, which are actually still very commonly used on powder diffractometers, okay? And on a powder diffractometer, we collect one-dimensional data anyway. So it really doesn't matter that we only have a point detector. For single crystal experiments, people did use point detectors, but they are rather slow, okay? Because basically you measure one reflection at a time. And you'd better know where to look for your reflections. You don't want to measure every point in reciprocal space, most of which doesn't have reflections in it, okay? There are 3 types of point detectors. Proportional is where gas atoms are ionized, and that is basically detected. Scintillation basically works through a fluorescence mechanism, then you have a photomultiplier. And then you have the solid state counters, which are actually very neat detectors. The solid state counter is a semiconductor based counter. What that one can do is, it can not only detect when X-rays hit, it can also discriminate energy. So, in contrast to many other methods where you need a monochromator to only allow one X-ray wavelength in, you can actually let all the X-rays from your copper or molybdenum or whatever source hit the detector. The detector will only count the ones that have the right energy. One of our instruments downstairs actually has one of these solid state counters. There's a big advantage if you work with any kind of elements that may start to fluoresce in the X-ray beam, because those wavelengths will not be exactly what they should be. Your solid state counter is going to ignore them, okay? So you don't get any background contributions from those. Most modern single crystal diffractometers will no longer use point detectors. They will use what is called an area detector. What that allows you to do is collect a portion of reciprocal space at once, okay? That's obviously a big advantage when you deal with a single crystal, where most of reciprocal space has no reflections, okay? Most diffractometers nowadays either use a version of an image plate or the so-called CCD, which is a charge-coupled device. That is actually what we have on the single crystal small molecule machines downstairs. Although Alan Pinkerton's instrument actually has a specialized image plate. Okay. So those are the detectors that you usually use. How do you set things up? Here's one of the oldest methods. Okay. The Debye-Scherer camera. It's a circular device. You have a little hole here where you can put a capillary in. That's your sample mount. You have a little collimator so that your X-rays are kind of nicely focused onto the capillary. You have a beam stop on the other side. And then you put a piece of film around the inside of this cylinder, okay? Very straightforward, very easy to machine. Put an X-ray source here, expose it, get your film out, and this is what it will look like, okay? And then you can measure how far are your lines on your film away from the direct beam, which is your origin of reciprocal space, right? And you know the diameter of the cylinder, and you can do your math and you can figure out the d-spacings. Very straightforward, very annoying to have to measure that stuff, right? But they could do that, you know, 70, 80 years ago. Not a big problem. How do you do an experiment nowadays? That looks more like what you would see nowadays. You use a powder diffractometer. And there are quite a few options, okay? One of them is what moves on the diffractometer. Do you have a theta-theta or a theta-2-theta diffractometer? Theta-theta means both the tube and the detector move. Theta-2-theta means your sample moves by theta, your detector by 2 theta, and your X-ray source stays fixed. What's the advantage? Well, you don't have to move an X-ray source. So mechanically, that's easier. What's the disadvantage? Well, if you run a powder sample and you start tilting it, if the powder isn't sticky, guess what? It'll fall off. Okay? You can have point detectors. This one is actually one of those solid state detectors that I was talking about. Or you can have area detectors. And area detectors can cover up to 120 degrees, like on this Enel diffractometer. So you have several options. And then you have options for how to mount your sample here. How about single crystal setups? Well, there are quite a few different methods that people used. The oldest one was Lowry photography. And funny enough, the oldest method is the only one that is still in use nowadays. Okay? Here's a setup of how von Laue actually did his first experiment. You have an X-ray source. You have a whole bunch of lead plates with little pinholes to just attenuate the beam. You have a crystal and you put a piece of photographic film behind it. And you get a spot pattern. Okay? That's how simple that setup is. It's even easier to machine than that Debye-Scherrer camera. You still use it nowadays for determining the orientation of crystals. So if you want to get phase indexing, this is the setup that you use. And we'll get into how that works a little further down, okay? What else do you have? Well, there were other methods introduced. Weissenberg, oscillation, precession methods. And these were really important methods when you still had point detectors on single crystal diffractometers. Okay? The reason for that was you didn't want to tie up instrument time with a bad crystal. So you wanted to first know, do I actually have a good single crystal before you ran a full diffraction data set? Because that data set could take you a week, 2 weeks, 3 weeks to collect. You can imagine that other people at your institution would be rather upset if you tied up the diffractometer for 3 weeks just to find out, oh, I should not have collected on this specimen to start with. Okay? Nowadays, where it is a day, people don't really care. Okay? 3 weeks, people do care. So, how do these old, no longer in use methods work? Well, all of them use monochromatic radiation. Okay? And what you do in the oscillation and Weissenberg techniques is you rotate a crystal around the axis of your mount by a few degrees. And you record the spot pattern that you get on film. Now, in most cases you'll just get something that looks like a mess. But if you align a crystal axis with this rotation axis, then you will actually get a series of straight lines of your spots. These are called layer lines. Well, that already tells you that in those days it was a pain in the behind to use these methods. You had to align a crystal axis with your rotation axis. Okay? If you have a big crystal that gives you some pretty faces, you might be able to figure it out. If not, life can be difficult. Okay? You try around until you get those layer lines. The Weissenberg method was very similar to the oscillation technique. The only difference was you had a metal screen that allowed you to select one layer line, and so you could actually move the film and get a better spot separation. One thing to keep in mind is, while these methods were useful, neither one of them gave you a direct view of the reciprocal lattice. Okay? As a matter of fact, this is what your data looked like. Then you had to apply all kinds of complicated equations to actually figure out what your crystal axis length was. Now, do me a favor, don't memorize those equations. Nobody uses them anymore nowadays. But I want you to appreciate how much further ahead we are with modern instrumentation. All the things you don't have to do anymore. Okay? So this is what you had to go through in the old days. Big step forward was actually a precession method. Once again, monochromatic radiation. In this case, the crystal axis precesses around the X-ray beam, thus the name. And the film is always kept perpendicular to the crystal axis. Now that means whoever builds that diffractometer has some work to do, okay? That requires quite some motors that talk to each other. So, mechanically very complex. The big advantage is this was the first method that gave you a direct view of the reciprocal lattice. Okay? So, you could actually figure out what the lattice was like, what the crystal system was. In some case you could look at systematic absences, figure out space groups. Okay? It was a big step forward. Of course, with modern diffractometers, once again, we really don't need that. But that was the historical development. Now, back to the one method that still is in use, the Lowy method. This is the only method that doesn't use monochromatic radiation. It actually uses white radiation. And that is why it is important that our lab sources have that white background. Okay? That's why we had to talk about that one. It makes use of that. Very simple setup, stationary crystal. Because in this case we fulfill the Bragg condition by changing the wavelength. We have all the different wavelengths coming in, right? Then we record a spot pattern either on film or on some kind of an image plate or CCD nowadays. And this is still useful because what you see in a Lowy pattern is certain symmetry elements. You see rotations and you see mirrors in Lowy patterns. So, anything that has translations you can see through systematic absences. The non-translational symmetry elements, rotations and mirrors, you can see in Lowy patterns. Okay? Somebody once asked me, how do you figure those out if you only see the ones with translation? Here's a method to get to some of them, okay? Now, here's a Lowy photograph, okay? This one was taken at a synchrotron, and it actually made it into a textbook. So you can already imagine that this is not what you will get if you take your own crystal and you put it on somewhere, okay? This is actually a very beautiful Lowy pattern. You see data quite far out, okay? And you do see that your patterns will usually not be ideal. There's some kind of background here, okay? So it doesn't look perfectly symmetrical. But this actually, you see all of these little, you know, rounded areas where you see reflections. This is certainly a very nice Lowy pattern. What does stuff look like in real life? Well, here's a real life example. There's scavenged from a friend. This is PBF2, so a much simpler system. The last one was actually a biological molecule. And this is what you will typically see when you take a shot at your crystal. A mess, in short. Okay? Spots all over the place. What's the reason for that? Well, when you put your crystal on there, chances are you don't have them aligned in any type of crystal axis towards the X-ray beam. Okay? So, you get a mess. You then, however, can reorient your crystal. And if you actually hit an orientation where you have a face with simple indices pointed towards your X-ray source, then you get something that looks a lot prettier. Like this one or that one. Okay? First one is unoriented, the second one is along the 100, and the third one is along the 110. PBF2 is cubic. Okay? And now we go back to that table of systematic absences that I sent you, and to the things that we skipped when we first talked about space groups. In that table of systematic absences, you have something that is called Lowy class. Okay? And what it will give you for cubic is two different Lowy classes, M3 bar and M3 bar M. It also gives you the full symbol, which is 2 over M 3 bar and 4 over M 3 bar 2 over M. Those are the only two Lowy classes in cubic crystals. Okay? Now, with that knowledge, let's look at these real-life patterns and figure out whether PBF2 is M3 bar M or M3 bar as a Lowy class. This is where it becomes important, all those little things that seem to be just kind of a waste of brain space so far. Okay? What are the symmetry directions in a cube? Now we all of a sudden need to know. What's the first symmetry direction in a cube? Could it be along the faces of the cube? 1, 0, 0? Is that a good one? It's actually a first entry for a cubic system. What's the second entry? Well, if you think about M3 bar M and M3 bar, it kind of gives it away, right? In what direction do we have threefold symmetry in a cube? Body diagonal, right? Body diagonal of a cube has threefold symmetry. What's the third symmetry direction in a cube? Some kind of a diagonal, right? And it's not the body diagonal, so let's just try the diagonal at 45 degrees to the faces, right? So those are our symmetry directions. If you look at the two symbols, M3 bar and M3 bar M, the second symmetry direction really doesn't allow us to distinguish these two Lowry groups, right? Because it has the same entry. The first and the last is what allow us to distinguish it. So the first one is either a 2 over M or a 4 over M. So they are already different. The 100 is already different in these two Lowry classes. And then one of these Lowry classes has no symmetry in the Lowry patterns along 110, while the other one has 2 over M symmetry along the 110. That's how you read these symbols, okay? So let's look at this. Here's the 100. Let's see whether we can find some symmetry. And keep in mind, this is real life data, okay? This is not calculated by a computer. Does anybody see any symmetry here? In the middle, what in the middle? Fourfold. Does everybody see that one? And as I said, this is real life data, so some people might say, well, there's no spot here, but there are spots here. It's real life data, okay? If this was calculated, yeah, there should be an equal spot over there, but it's not calculated. So it might just be that the detector was shaded a little bit or something like that, okay? So, fourfold symmetry. Anything else? Mirrors. And Chris claims I have a mirror here, and I have a mirror here. And of course it should be right on top of the spots. And I am offered the diagonals. Does everybody see these? Everybody agree? So, what is that symmetry? Looks more like the 4 over M, not the 2 over M, right? So we really wouldn't need to look at the 110 anymore, right? Because we already know what it is. But if it is M3 by M, then the 110 should show twofold symmetry. So the question is, does it? And a lot of people are nodding. Sure enough, it does have twofold symmetry. Once again, you're missing a spot. I think in this case it's actually because it would be off the plate. Okay, so you just happen to not measure it. This one is not fourfold symmetry because these spots are at a different distance than these. Okay? Do I have mirrors here? I have mirrors in these directions. And some people might be tempted to draw a diagonal mirror here. Nope, there is no diagonal mirror. Because diagonal would actually go in this direction, okay? At 45 degrees. That would be the diagonal. That doesn't go through the spot. The spots are not on the diagonal. Which means I should get a second spot here. So no, there's no diagonal mirrors on this one. So there's our 2 over m, right? So we've identified the Lowry class of our PBF2, haven't we? It's M3 by M, because we see 4-fold symmetry in the 100 and 2-fold symmetry in the 110. Now, why would anybody care? It's a good question, right? Because it might be on the exam, that's a good answer, but why would anybody care in real life? Well, remember how we went through systematic absences and how some people said, so do I have to list all of these groups? Here are the reflection conditions for PBF2. Let's see whether we can figure out in which line of the table we have to move. You have your own tables, plus this one is in your handout. So everybody take about a minute and try to figure out what line of this cubic table is actually the line where PBF2 would fall, based on its systematic absences. You found something? Let the other people find something too. Alright, let's look at it together. In this case, life is pretty easy because things are kind of listed in the order in which you can look at them. Okay. First condition, HKL, H plus K, H plus L, K plus L. What does that designate? Phase centering, right? If you look at it, that gets us into this part of the table. All of these space groups start with an F. Okay? So our first condition already really cuts down where in the table we are. OKL has K comma L. So we look at this part, okay? And 3 out of these 5 lines have the K comma L condition. These 2 have the K plus L equal 4n and K and L conditions, which we obviously don't have. Then we have HHL, which is H plus L. That leaves us with those 2, right? Because the third one would have H comma L. And then we have the OOL equal L condition, which is right there. So we are left with one line, the F dash 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 symbol. Okay? If you look at that one, there are 5 entries in that line. 5 possible space groups. Okay? They cannot be distinguished based on systematic absences. Now, nowadays you have computers. Big deal, right? However, in the old days, when you did everything by hand, would you have liked to attempt a crystal structure solution in 5 different space groups? Probably not, right? If you can do anything to help yourself out, you'll do it. Well, here's one way to help yourself. You figure out the Lowry class of your crystal. That means instead of 5, you either have 2 or 3 left, okay? In this case, we are left with 3, because we know that our Lowry class is M3 by M. So it has to be F432, F4 by 3M, or FM3 by M. As a matter of fact, if you ever chose to look it up, PbF2 crystallizes in FM3 by M, okay? So that is how you can use these Lowry photographs together with some systematic absence data to really narrow down your choices of space groups. And of course, in some cases, people want to measure properties of crystals along certain symmetry directions, and that is where the Lowry photography comes in. You need to know what your phase index is in order to determine what the properties of this crystal are, right? So most of the time, people work with some pretty big crystals, and they're fairly easy to orient. Does that make sense? Neat little application, isn't it? And all of a sudden, some of these things actually fall together. That's why we had to go through some of them. What does a single crystal diffractometer look like? Here's your pulling it all together picture. Basically what you have is you have an X-ray source, goes onto a crystal, which is mounted on a goniometer head, which gives you some rotational degrees of freedom of the crystal. That whole thing is mounted on a circle that can also be rotated. But once again, your crystal stays here. It's at the center of the circle. You can also rotate that one in this direction, or you can move your detector. You always have a beam stop. So what you really have is a whole bunch of rotational degrees of freedom. That is what allows you to image large parts of reciprocal space without having to move either your X-ray source or the location of your crystal. Okay? The crystal will still move. It's being rotated. The detector might move depending on your setup. The X-ray source stays fixed in this case. A couple of more words about the single crystal diffraction setup. Nowadays. The modern one. That was a modern diffractometer, okay? Well, actually no, not quite, because this detector would be a point detector. If you have an area detector here, that would be what a modern diffractometer looks like. Single crystal experiments use monochromatic radiation. Most instruments for small molecule crystallography will use molybdenum. For macromolecules, you usually find either copper or chromium. Nowadays, copper is more common. Reason for that is you have much bigger unit cells, so you get many more reflections, and you want to be able to resolve them, okay? Yes, you want to measure enough reflections, but if they start sitting on top of each other, you really don't win. How do you usually do your experiment? Well, you usually start with what is called a rotation matrix, okay? And Chris is nodding, he has done that already probably. So you put a crystal on, you tell the instrument to collect a matrix, and that is the reason why nowadays we no longer do those Weissenberg oscillation precession methods, okay? That matrix, 60 to 90 frames, exposure time depends on how strongly your crystal scatters. It takes you what, about 15 to 30 minutes to get that one done. The system will then try to index that rotation matrix. That means it will see, can I actually fit all of these spots into a simple unit cell? If it succeeds, then you have some idea of what your crystal system is, what your unit cell size is. You can check whether that is a known compound, okay? Let's assume you do a reaction. You have two starting materials, you want to get a product. You know the crystal structure of the starting materials. Guess what? Might be worth quickly checking when you get an index on your matrix whether that happens to be one of your starting materials. Okay? You can do a quick database search. Is this a known cell, and is the composition something that could be in my sample? In that case, it's not worth collecting. Another thing, if your computer cannot index that matrix, it's probably not worth collecting on the crystal. Okay? Because if you cannot index your data, you cannot solve the structure. And there might be tricks that you can play, throwing certain reflections out. Better thing to do is look for a different crystal. Find a crystal where the matrix indexes cleanly. Okay? Why might the matrix not index cleanly? Well, you could have several crystals mounted. What are warning signs for that? First of all, if it cannot index a large number of reflections, that would be a warning sign. Sometimes it's more subtle. Okay? One of the things you want to check is your spot quality. We know from our derivation of reciprocal space scattering that you should have nice single spherical spots if you have a single crystal that has a decent number of repeats in all 3 dimensions. Right? That was the solution of our general scattering equation in 3 dimensions. If you have streaky spots or shoulders, something is wrong. Okay? Could be defects, could be twins, could be cracks in the crystal, could be all kinds of things. Fact is, you shouldn't see that if you have a good single crystal. Okay? What do I mean by that? These are integrations through a spot. Okay? That's the only way to really judge your spot, because the spot on the screen is going to look like a bright blob. Okay? But you can integrate across the spot. This is what I would call a good spot. If you get this, that's really a split reflection, okay? To your eye, this just looks like one bright thing. But if you look at the intensity profile, this is not okay. That's not a single spot. Another way of judging it, even if you don't get that dip, is do all the spots have about the same width? Okay? Even if I didn't have this dip, if this thing was twice as big as that one, width-wise, something is wrong. Okay? They can't both be the same type of single spot. So, those are warning signs. If you see that, pick a different crystal. You don't see that, you usually collect the full data set. Exposure time depends on your crystal. If it scatters strongly, you might be collecting 10 seconds per frame. If it scatters more weakly, it might be 30 or 60 seconds. You might be pushing it to 120. I wouldn't go beyond that in most cases, okay? That's when you have that trade back between what can I actually detect with the exposure time, because your background also goes up the longer you expose, of course. The number of frames will also depend on your crystal symmetry, okay? And the program usually has some defaults in. And at the beginning, your first few crystals, you'll be working with a more experienced crystallographer anyways, who can kind of give you these insights. Oh, this is that in that system. We should certainly collect this many frames in that quadrant of reciprocal space, okay? They have experience with that. Listen to them. Ask them some questions. You know some about reciprocal space. These things will make sense to you, okay? Because you now have some idea of what these things mean. Now, why do you go through this class if the computer does most of the work for you? Well, sometimes the computer fails, okay? That is when it's important to know something. For example, your single crystal program might have managed to index, but it doesn't propose a space group to you. Dang. What now? Systematic absences might not be enough, or it may just not have enough reflections to be confident about making a choice, okay? Or maybe you would actually like to have some idea of what your crystal system is before you start collecting your matrix. Maybe you know that there's an impurity phase in your system that is cubic, which you don't expect for your product, okay? Do you have to collect a half-hour matrix to find out? There are actually other options, okay? There's something called a rotation frame, where you do a full crystal rotation and you get a spot pattern, which allows you to see rotation axes and mirror planes. So it's kind of similar to what you get out of a Lowy setup. You get some view of the reciprocal lattice. So you can get some kind of idea of the Lowy class from a normal single crystal diffractometer too. So in these cases it might help if you are able to look at symmetry yourself. Okay? There are times when you have to do that. In the ideal world, with an ideal crystal, Yeah, the program's going to do most things for you. But trust me, life is rarely ideal. There will be times when you have to interact with your data. If you go into protein crystallography, you certainly have to do quite a bit of work. It's not quite as automated. If you deal with powders, you certainly have to do some crystallography and some work, okay? So, that is your first introduction to data collection. It's quite a lot of stuff. And none of you will be doing all of these things, okay? You usually specialize in some area. But likely, most of you will be doing some of these things. Hopefully, you will, and hopefully you'll get some good results, okay? It's actually quite a good experience if you actually have a single crystal and you can figure out what that structure is. It's a flavor. It gives you an overview of things that are out there. I don't expect you to walk up to a diffractometer and do your experiment all by yourself. But you know enough now that you can talk to somebody and with their feedback design the ideal experiment for whatever you are doing, okay? And that is the goal of this class. Are there any questions about data collection at this point in time? If not, on Wednesday we'll be meeting here and start having a look at indexing for powder data, which, as you will find out, is not a push-the-button automated approach, okay? And yes, you got spoiled, I know, Christoph. But you will find out that it can involve quite a bit of work. And it will also teach you how important it is to collect good data, okay? Because the data that I'm giving you is on purpose non-ideal data. You'll have to do a couple of additional steps, and it will teach you forever that you want to make sure you collect the best data you can. Because probably you'll spend most of the first class just trying to correct for the errors in the data. And yes, once you go through it, after that, you'll always make sure that your diffractometer is in good shape. If there are no other questions, that's it for today, and I'll see you on Wednesday.